Consider a spring mass system where we treat the mass as a particle and then we stretch the spring such that the mass ends up at a position of x equals a from the equilibrium position. And when we release the mass, it oscillates back and forth from x equals a to x equals minus a. And when the mass is somewhere to the right of the equilibrium position of the spring, then the spring develops a restoring force that points to the left. So applying Newton's second law, we have force is equal to mass by the acceleration. So when the position of the mass is to the right of the equilibrium position of the spring, x is positive and the force and acceleration are in a negative direction. Now doing some algebra, where x with two dots is the acceleration or the second derivative of position with respect to time. And we define the ratio of the stiffness of the spring to the mass as omega squared. And we'll be looking at these quantities in more detail that describe the physical characteristics of the system. The solution to this differential equation, which we derived, that describes the simple harmonic motion of a spring mass system, can be written as follows, where x describes the position of the mass at a particular time t. So these quantities are all constant except for the variable t. And a is the amplitude of the oscillation, where the mass oscillates between x equals a and minus a. Omega is the angular frequency, and phi 0 is referred to the initial phase. And therefore the entire quantity in the parenthesis is called the phase angle. So the solution to this differential equation is a periodic function because this oscillation of the system goes back and forth forever, as we don't consider drag or friction between a block and a surface. And you can verify that this is a solution to the differential equation by differentiating twice and substituting it back into the original differential equation. Here are several solutions plotted using this equation for simple harmonic motion with different initial conditions. So for example, for this case, we can stretch the block to the amplitude a and then hold it at a velocity of 0 and release it. So the amplitude of the oscillation is the maximum position of the block from equilibrium. Now the period of the oscillation is defined as the time taken for the block to complete one cycle. So in this case, it starts at a position a, goes to minus a, and returns back to its original position. So that takes 4 seconds. And the frequency of the oscillation is defined as the number of cycles per second. So here the block completes one cycle every 4 seconds. So this is 0.25 cycles per second, or hertz. And the angular frequency is in radians per second, so we multiply the frequency by 2 pi. So here we can observe the following relationships between these different quantities. And we'll look at the initial phase next. Different solutions for simple harmonic motion can be visualized using a circle. And these all have the same amplitude of oscillation of 5 centimeters and the same angular frequency, but a different initial phase. And let's take the green case as an example. So the spring is stretched such that the block is 2 centimeters from the equilibrium position, and then the block is given an initial velocity, which is the slope of the tangent to this curve at a time of 0 seconds. We have an initial phase of 0.41 radians, and where t equals 0, if we take the sine of this angle and multiply it by 5 centimeters, well, that gives this vertical distance over here, which is 2 centimeters. Now at a time of 1 second, we simply add pi on 2 to the initial phase, so we're basically just adding omega t. And therefore taking the sine of the phase angle gives the next position of the block, which is close to the amplitude of the oscillation. So we can see that each block lags behind the other, and that's what the initial phase represents. As we've seen, simple harmonic motion can be started using different initial conditions. So if we differentiate this equation, describing the position of the mass versus time, we obtain a velocity. And here we can apply some initial conditions, so initial position at time 0 and the initial velocity at time 0, which gives the following from these two equations. So from the initial position, we can determine an expression for the initial phase. And if we square these equations on both sides and divide the second one by omega squared and add them together and square root both sides, we can obtain an expression for the amplitude. And therefore simple harmonic motion can be initiated using different initial positions and different initial velocities. Given a graph that describes the motion of the harmonic oscillator with these properties, let's calculate the quantities that describe the physics of the system. So the angular frequency is the square root of the stiffness of the spring on the mass of the block. And the frequency is omega on 2 pi, which is in cycles per second or hertz. And the period is the reciprocal of the frequency, or 2 pi on the angular frequency. which is around 2.1 seconds. And the initial phase is the arc sine of the initial position on the amplitude. So therefore we can write an expression for the position of the block as a function of time, which is the amplitude by sine of the angular frequency multiplied by time plus the initial phase. And I'll leave it for you to find the velocity at time 0 by differentiating this equation. We have the position as a function of time of a spring mass system undergoing simple harmonic motion, and if we differentiate this with respect to time, we obtain a velocity. And differentiating again gives the acceleration of the block. And from the graph, we can obtain the period of the oscillation, which is the time taken for the block to complete one full cycle. So that will be around 2.1 seconds. And therefore the angular frequency is 2 pi on a period. And the initial phase is 0 because the block starts from a position of 0. And we can also observe the amplitude of the oscillation, which is around 5 centimeters. And because this is the undeformed position of the spring, the acceleration of the block is 0 at time 0. And when that block reaches the amplitude of the oscillation, you can see that the acceleration is at a minimum. So it has the largest magnitude, but points to the left, because the force in the spring is a restoring force. And at this point, the velocity of the block is 0. Now have a go at interpreting these motion graphs. Suppose we let this block settle slowly under its own weight from the equilibrium position of the spring. So when the system is in equilibrium, the block has moved a distance of ye, and then we have a force developed in the spring that balances the force of weight. And by Newton's first law, we have the following expression. Now suppose we give this block some initial velocity, and we'll measure y from the equilibrium position of the system. So we have the following forces acting on the block, and this time the force in the spring is k by ye plus y. So by Newton's second law, the net force on the block is equal to the mass by the acceleration of the block. And doing a bit of algebra, and from this equation, the expression on the right is 0, so we obtain the following differential equation. And dividing through by m, we can write this in terms of the angular frequency, and therefore we can use the solution we derived for the horizontal harmonic oscillator, which has the following form. Suppose we have a block attached to two springs in parallel, and we give it some initial condition, and the block oscillates at some amplitude a. Therefore the forces in the springs are restoring forces, and are generally not the same magnitude because the springs have different stiffnesses. But because we treat the mass as a particle that only translates on this frictionless surface, so we would visualize these forces passing through the center of mass and not producing any torques. So therefore the springs would deform by the same amount that the block displaces from equilibrium. And that gives us the following equation of motion. According to Newton's second law, we can rewrite the equation as follows, and then dividing through by the mass, and designating the term in the numerator as the effective stiffness, and designating this term as the square of the frequency of the oscillation, then we can use the same solution that we derived for a harmonic oscillator with a single spring. We have a harmonic oscillator with the springs in series, and applying some initial condition to the block, we make it oscillate at some amplitude a. And taking a free body of the mass and the springs, the force acting on these components has the same magnitude, because we treat the springs as massless. So therefore the force in the springs can be written as follows, and the total deformation of the springs is equal to the displacement of the mass from the equilibrium position. So from this equation, and if you do the following multiplication and do some algebra, so applying Newton's second law on this block, and then doing a bit of algebra, and designate this as the effective stiffness while dividing through by the mass, and then if you designate this term as the square of the angular frequency, then we can again use the same solution that we derived for a horizontal harmonic oscillator with a single spring. Suppose we have a mass attached to springs in parallel and springs in series, and it's given some initial condition that makes it oscillate at some amplitude. So if the block moves to the right, we have the following effective stiffness of the springs in series and the effective stiffness of the springs in parallel. So these are restoring forces that draw the block towards the equilibrium position. So recall that we derived the effective stiffnesses of these systems where we can treat them as a single spring. So for the parallel springs, we just add their stiffnesses together, and for the springs in series, we had the following expression. So therefore the effective stiffness of the system is the sum of these stiffnesses. And again, we can write our equation of motion as follows, where the square of the angular frequency is the effective stiffness of the system on the mass. If we consider a simple pendulum where we have a mass attached to a massless rod that swings through some angle theta. So we have a restoring force being the force of weight acting on the mass. And if we take a sum of torques about the hinge, the force of weight by the moment arm, and that's equal to the moment of inertia of the mass by the angular acceleration. Now you can get the same result by resolving this force into normal and tangential components. So if you take a sum of forces in the tangent direction, which is the same thing as L by the angular acceleration. Now if you do some algebra, and you can't solve this analytically, so we'll apply the small angle approximation, and therefore we can write the equation in the following form, where the square of the angular frequency depends on the gravitational acceleration and length of the rod. And now we can apply the same solution that we derived for a horizontal harmonic oscillator. Consider a physical pendulum that swings about a hinge located at P by an angle theta. So we call this a physical pendulum because we're actually modeling the physical body, in this case being a bar. So this bar has a force of weight acting at the center of mass, which is located at a distance of L on 2 from the edge of the bar. So taking a sum of torques about the hinge, the force of weight produces a restoring torque. So here the moment arm has the length of L on 2 sine theta using this right triangle. And that's equal to the moment of inertia of the bar about an axis passing through its endpoint multiplied by the angular acceleration. And now doing some algebra and using the small angle approximation where the bar swings to a maximum angle much less than 1, then we can approximate sine theta. And this quantity is the square of the angular frequency. So again we can use the solution for a harmonic oscillator with one spring that's oscillating horizontally. Here we have a torsional pendulum because there's a torsional spring at point P, so we have a force of weight acting at the center of mass. So this produces a restoring torque about point P, which is equal to the force by the moment arm. And we also have the torsional spring with a stiffness of Kr that provides resistance to rotation. And that's equal to the moment of inertia of the bar about its endpoint by the angular acceleration. So we can again apply our small angle approximation. So sine theta will be approximately theta. Then dividing through by the moment of inertia, and now we can group the terms on one side of the equation, and therefore we can write this as the square of the angular frequency, and therefore the solution to this second order differential equation will have the same form as that of a harmonic oscillator with one spring that oscillates in a horizontal direction. Given a harmonic oscillator on a horizontal surface, the total energy of the system is the sum of a kinetic energy term plus the potential energy stored in a spring. And when the mass reaches a distance of x equals a, being the amplitude, from the equilibrium position of the spring, well, the total energy is then equivalent to the potential energy of the system. And we can show this by using the solution to the differential equation, which we derived as follows. And if we differentiate this, you'll get an expression for the velocity of the block. So these expressions can be substituted in a total energy equation. And as we know, the square of the angular frequency of the system is equal to the stiffness of the spring by the mass of the block. So therefore we can write m omega squared as k. And now if you factor out 1/2 ka squared, and using the trig identity, the term in the brackets is 1, and therefore the total energy of the system is equivalent to the potential energy when the block reaches the amplitude of the oscillation. We can also show that energy is conserved for a vertical harmonic oscillator. So the total energy is the sum of the kinetic energy of the block plus the potential energy stored in the spring. So when the block reaches some distance y from our system's equilibrium position, the spring gets stretched ye plus y. And then taking this as our reference point, we can subtract the gravitational potential energy, which is mgy relative to this point. And note that there's a loss of gravitational potential energy because the block displaced in the direction of the gravitational force. Now if we differentiate the energy with respect to time, we can apply the chain rule. And now if you factor out the velocity, we obtain the following expression. And when we applied Newton's second law, we found that this equation of motion was equal to 0, and by Newton's first law, we found that this expression was also equal to 0. So therefore this derivative is 0, which means that the total energy is a constant. and therefore energy is conserved. For a simple pendulum, the total energy consists of the kinetic energy of the mass, which is 1/2 by the moment of inertia by the square of the angular velocity, and plus a gravitational potential energy term. So note that the mass is displacing by some amount against the gravitational field. So by trigonometry, we can obtain this distance, which is L cosine theta, and then subtracting this from the length to the center of mass gives the following expression for the gravitational potential energy. And now we can differentiate this expression with respect to time, applying the chain rule. And now factoring out the angular velocity, we recognize that this is the equation of motion for the pendulum, which is equal to 0. So therefore the total energy is constant, and energy is conserved in this system. Block A is attached to a spring, and block B is initially at rest, and the spring is compressed to half its equilibrium length, and when it's released, block A collides with block B at the instant when the force in the spring is 0. Now assuming a perfectly inelastic collision, write the velocity of the blocks just after impact, in terms of the velocity of block A. So applying the conservation of momentum, because there's no horizontal force acting on the system, now write the amplitude of the oscillation before and after the collision. So before the collision, the amplitude of the oscillation is L on 2. And after the collision, we'll apply the conservation of energy, where the kinetic energy of the system is converted fully into potential energy when a new amplitude of the oscillation is reached. And before the collision, you can also apply a conservation of energy, and then from these two equations you can complete part B. And I'll leave it for you to write the angular frequency and period before and after the collision. A physical pendulum with a uniform bar of mass m and length L swings about a fixed axis through P. And first we'll determine the torque produced by the bar and the sense of the torque about P. Well, we have the force of weight acting through the center of mass and a vector from the pivot point to this force, which has a length of L on 2. So effectively the torque by the right hand rule is negative, the force by the moment arm, and the vector has a direction into the screen. Now the equation of motion states that the net torque about P is equal to the moment of inertia about P by the angular acceleration. And doing some algebra, we can rewrite this as follows. And using the approximation for small rotations, we can rewrite the equation of motion as follows, and therefore the angular frequency is as follows, and the period of the oscillation is 2 pi on the angular frequency. A bullet is fired at a block, and it becomes lodged in the block when it's a quarter way of the amplitude through the oscillation. Now write the velocity of the block immediately before and after impact, in terms of the following variables. So applying a conservation of energy before impact, and from that you can solve for V. Now after impact, if we isolate the entire system, the bullet does not contribute to the horizontal angular momentum of the system, and the entire system is not subjected to an external horizontal force. So therefore, the momentum of the block is equal to the momentum of the system with the bullet lodged in the block. And you can solve for the velocity after impact. Now write the frequency of the oscillations before and after impact in terms of the following variables. So the frequency before impact and after impact, and write the amplitude of the oscillations after impact in terms of the following variables. So applying a conservation of energy, and now you can solve for the amplitude by substituting the values we found from part A. A block is attached to a spring with a ball resting on it, and the spring is compressed to half its length and released, and the ball leaves the block when the spring reaches its equilibrium length. So treating the ball and block as a particle, if we initially leave the spring to settle under the influence of gravity, and we measure the oscillation from this position. To find the launch velocity of the ball, we have the elastic potential energy, and taking our reference position at the equilibrium of the spring, we're at the gravitational potential energy, and that's equal to the kinetic energy of the system, and from that you can solve for the launch velocity. Now calculate the maximum height of the ball relative to the launch position. We're using the following kinematic relation, and we can solve for the height. And write the equation that describes the position of the block on the ball as a function of time before the ball leaves the block. We'll recall our solution to the harmonic oscillator, and the initial phase must be minus pi on 2, because the block starts at a compressed position of the spring. Suppose we conduct an experiment where we have a pendulum with the same mass attached by massless strings which have a different length. And then we'll let the pendulum swing through small angles and record the period of the oscillation using a stopwatch. Now if we square both sides of this equation and divide through by the length, then we get a constant on the right hand side. So therefore squaring the recorded periods for the pendulums with a different length here, and then dividing through by the length, we obtain the following results. Drawing the line of best fit through the points, and taking a slope of this line will give you a constant. So as you can see, these constants are close to this actual result that we derived using our equation for simple harmonic motion. We're increasing the length of the pendulum, increases the time taken for it to complete one cycle, and increasing gravity will cause a larger restoring force, which reduces the period and thereby increases the frequency and makes it oscillate back and forth faster. To derive the solution to the second order differential equation that models simple harmonic motion, we take a guess using an infinitely differentiable function with repeating derivatives. So e to the power of some constant by time. And if we differentiate this twice, we get the velocity and acceleration. And if we substitute back into the original differential equation and factor out e to the lambda t, and for a non-trivial solution, the term in the brackets is 0. So if we square root both sides, we get the following result. So the solution to this differential equation is a superposition of two solutions, which involves a constant by the first solution plus another constant by the second solution. And this solution is unique for this second order differential equation with constant coefficients, and we can manipulate this solution in different ways using trigonometric functions. Using Euler's formula, we can derive an alternative solution to this second order differential equation that models simple harmonic motion. So if we substitute for the exponential terms, and if we group the cosine terms and the sine terms, well, these are both real constants. So therefore we can write the solution as some constant by cosine omega t plus another constant by sine omega t. So for example, we may have two complex numbers that look something like this, and if you add them together, you get a real, and if you subtract them from each other, you get an imaginary number, and then multiplying this by the complex number I will give you back a real. We can write this solution to the ODE modeling simple harmonic motion in an alternate form. And this is valid because if we apply the addition trig identity, we can write this as follows, and then doing a bit of algebra. So effectively this here is a constant, and this here is another constant. And you can verify that this is a valid solution by substituting it into the ODE.